Hey everyone, welcome back to the Summer Pi series, and in this video we'll finally be getting into some background behind neural networks. But don't worry, we won't go too deeply into the math. My goal is just to provide an intuitive explanation so you could understand what's going on when we start building them. Neural networks have been around for quite some time. They were first proposed in 1944 by Warren McCulloch and Walter Pitts from the University of Chicago. The theory would fall out and then come back in fashion multiple times, but two things enabled the seemingly permanent return of neural networks, and that's the availability of data and high-performance computing through GPUs and parallel processing. So let's start building an intuition on how they work. Here we have an image of a neural network. Every circle is called a node, and the nodes make up their layers. Nodes are connected to the nodes in the next layer through these arrows which contain our weights. This is a type of network called a fully connected neural network since each node connects to every node in the next layer. Here we have our input layer, then we have our hidden layers, and then we have our output layer. And our output layers are aimed to provide the desired results, such as whether something is a hot dog or not a hot dog. Let's say we want to determine whether or not we might have a certain disease. Our network begins with our inputs. This could be a good diet, family history, and age. But of course, health is more complex than this, but I'm just trying to keep it simple for now. The data could be read as follows. 1, as in we follow a good diet. 0, as in there's no history of family diseases. And then we have age at 19. You might be a little concerned that the scale of this number is completely different than the others, but this is something that normalization, such as the standard scalar function we used, aims to address. So let's say the scaling function turned this number into a 0.19. We also have our randomized weights, which is the 0.6 for weight 1, 0.2 for weight 2, and 0.5 for weight 3. And each of these black arrows have their own unique weights. Now the process starts with a forward propagation. We start by multiplying each of the inputs with their corresponding weights, and then we add them up. You could think of this as using our knowledge to create more interesting features or building blocks. Then we add a bias. An intuitive way to understand this is to imagine you're trying to make a decision, maybe whether or not you want to go out with your friends. Deep inside, you have this bias that says, I want to hang out with my friends, but then you need to consider the other variables such as, do you have money, do you have other responsibilities to take care of, and etc. Another way to think of this is to notice that this equation can be written in the following form. And this form looks exactly like the equation for a line if you think of y equals mx plus b. So then the bias just really helps complete this similar expression. Finally, we apply a nonlinearity or activation function. So we just discussed how this equation looks a lot like the equation for a line. The problem is that this is too simple. We can allow for more complexity by applying these nonlinearities. The three most popular are sigmoid, tanh, and ReLU. I won't dive too deep into them right now, but I will explain how I choose between them when we start building our neural network. For now, just understand that these functions help the network to understand more complex representations. And in this explanation, I'll use the tanh function. This whole process is repeated for all the nodes in the layer. Then we repeat this process for nodes from hidden layer 1 into hidden layer 2. Here we're using our new building blocks from hidden layer 1 to build a new set of features in hidden layer 2. As you propagate through the hidden layers, you are essentially building higher level features. And then the features in this final layer, of course, are the most complex ones used to determine the output. This whole process is applied to all of your training samples. The really confusing thing about neural networks is while we cannot exactly understand what it's learning, we can be confident that it's learning something useful. It's the math that drives this process that is so simple, and understanding it will provide insight as to why they work so well. So once you compute the output, you compare it to the expected value. We use powerful statistical methods to compute this error or loss, such as cross-entropy. The equation for binary cross-entropy might look a little scary at first, but let's pick at the key details. In my opinion, the most important detail from a very fundamental standpoint is the use of a log function. Because the log function penalizes the model more severely, the more incorrect its prediction is. So here we have a graph of the log function, and you'll notice that the further we stray away from 1, the steeper and steeper the graph gets, which means the model is more impacted for more incorrect predictions. By using the log function as the basis for error analysis, the model becomes more suitable for steering the learning process towards the right direction. So let's say that despite having good health and a young age, the model predicts that you will have a disease with 0.8 or 80% confidence when our expectation is 0 or no disease. Then solving this equation gives us the following result: 0.70, which is a pretty high error. But then let's say our model actually performs pretty well and it predicted a 0.15 or a 15% confidence. Then our error is 0.07, which is significantly lower. Your total error is the sum of the errors for all of your training samples. Once you have this error, what do you do with it? Since this is a more low-level explanation, I won't review all of the math, but I might do so in a future video. Just let me know in the comments if you'd like to see that. But anyways, we're going to backpropagate this error, checking for how the loss changes as you change the weights. These changes are called gradients, which is why backpropagation is essentially gradient descent. Obviously, you want to move in a direction that will reduce your error, so your weights are adjusted to reflect that. This process is repeated for a desired amount of iterations. So you backpropagate your loss and then you update your weights. Now a little more info on how gradient descent works. You start off with a certain error, but as we backpropagate our errors, we take steps towards the right direction. We want to go and minimize our loss. And this is represented through this expression. So P2, we have our updated weights, P1 our current weights. Then we have this gamma sign, which is our learning rate, which determines how quickly our model will learn. But you want to be careful not to set this too high, because you could kind of compare it to when you try to study too many things at once and try to learn too many things at once, you're not really going to retain anything. So that's similar to what happens if you make a learning rate too high. Then we have this expression, loss of P1, which determines how loss changes with our current weights. Now some of these variables are bolded for a reason, and it's because each of the weights have their own direction. They will increase or decrease based on how they respond to the loss function. So we bold these variables just to give a sense of vector, just to show that they each have their own independent directions. But anyways, as we go through the training run, we're going to continue to take steps, and these steps should become smaller and smaller as we approach our global minimum. So just some additional elements that add to the power of neural networks are that the features are independent of each other. You might have noticed that while this is a fully connected network, the nodes within a layer are not connected at all. This reduces the amount of redundancy. We want to have as much unique information as possible, and it's less useful to have multiple variables that essentially mean the same thing. Just because these features are composed of the same variables though, that does not necessarily mean that they're dependent on each other. This could be studied in differential equations, but we won't go into it here. So if we can't understand what exactly it's learning, if we can't understand what the numbers mean within those hidden nodes, how can we be confident that they work? How can we be confident that they're learning something useful? So first off, we had the nonlinearity through activation functions. This allows us to have more complex representations. Next, we have our independent features. We remove the redundancy of information. We use powerful statistical methods which have been proven for a very long time. This includes the entropy and binary cross entropy and mean squared error. Entropy is normally used in classification, while mean squared error can be used in predictive modeling type of questions such as stock trading. Then we used gradient descent and backpropagation, the idea that you're tracking your errors and adjusting for them constantly. And lastly, they're biologically inspired, and while this is a more philosophical standpoint, nature is a great source of inspiration for developing engineering solutions. They provide living things with some of the most complex yet powerful mechanisms. While it's unclear what exactly the neural network is calculating, the mathematical backbone makes it seem almost unsurprising that it's become as successful as it has. And with that said, I hope you enjoyed this video. I hope you learned a lot about neural networks and at least became more confident in being able to use them. In the next video, we'll start to create a neural network in Python, which will help us automatically process the LSST data. So I hope to see you there. Bye.